Welcome to this presentation on elastic neutron scattering. My name is Jan Leen Kloosterman and I work at the Faculty of Applied Sciences of Delft University of Technology in the Netherlands. In this lecture, we will derive an analytical expression for the energy loss of a neutron in an elastic collision with the target nucleus. The theory is quite complicated, and therefore we will make some approximations to simplify things a bit. The main assumptions we will make are: first, only two particles are involved, a neutron and a target nucleus. Secondly, the target nucleus is assumed to be initially at rest. Third, the theory is valid only for elastic collisions. This means that the target nucleus remains in its ground state after the collision event. And fourth, we will assume isotropic scattering in the center of mass system. This is usually a very good approximation for scattering of neutrons with light nuclides. Before we continue, we have to define the concept of space angle. Assume an area dA as shown in the figure. The area has two sides, the red side, which is v d theta, and the blue side, which is v sine theta d phi. Here, theta is the polar angle between the z-axis and the v vector, and phi is the azimuthal angle, both shown in the figure. Now dA is the product of the two sides and equals v d theta, v sine theta d phi. Instead of sine theta d theta, we will write d cosine theta. And as a shorthand notation, we will use mu for cosine theta. So the area becomes v squared d mu d phi. Now by definition, the space angle is defined as the area dA divided by v squared and equals d mu d phi. You can easily check that the integration over the whole phase space 4 pi, which means integration over 2 pi for the angle phi and integration over pi for the angle theta, or 2 pi for phi and from -1 to +1 for mu, equals 4 pi. Now imagine we have a neutron colliding with the nucleus, indicated here with the orange sphere at the center of the plot. The neutron before the collision has energy E and direction omega, while after the collision it gets an energy E prime and direction omega prime. Usually E prime will be less than E. The probabilities to scatter from E to E prime and from omega to omega prime are usually coupled to each other. However, the scatter probability will usually not depend on the actual incoming and outgoing directions, but only on the angle between these two directions. This angle is indicated with theta in the figure. The scatter probability will usually not depend on the azimuthal angle phi. So the scatter probability to scatter from E to E prime and over a certain angle theta, indicated here with mu, and over a certain angle phi, will usually not depend on phi and can be written as a probability to scatter from E to E prime and over a certain polar angle theta, indicated here with mu. We can express the kinematics of neutron scattering in two reference frames. the laboratory system and the center of mass system. In both systems, the total momentum of all participating particles is conserved. For elastic collisions, however, also the total kinetic energy of all participating particles is conserved. In the center of mass system, the observer moves with the center of mass itself, and the total momentum of all particles is zero. In the center of mass system, the neutron energy does not change, only its direction changes. This means the scattering in the center of mass system is usually much more isotropic than in the lab system, and that the kinematics are much easier described in the center of mass system than they are in the lab system. But of course, as a final result, we want to know the energy transfer of the neutron in the lab system, which means that we have to relate the kinematics between the two reference systems. In the following slides, we will therefore derive expressions to relate the energies and the scatter angles in the two reference frames. In this figure, taken from the book of Duderstadt and Hamilton, we see the velocities and scatter angles in the laboratory system, the upper two plots, and in the center of mass system, the lower two plots. In the lab system, we have energy transfer from the neutron to the target. And usually the velocity of the neutron after the collision will be less than the velocity of the neutron before the collision. In the center of mass system, there is no energy transfer from the neutron to the target, and we have only rotation of vectors. So there the velocity of the neutron after the collision equals the velocity of the neutron before the collision. We will now relate the velocities before the collision in the lab system to those in the center of mass system. All velocities on this slide are the absolute values of the velocities. First we will calculate the velocity of the center of mass itself. This is by definition equal to the total momentum of all participating particles divided by the total mass of all particles. And because we have assumed that the target nucleus is initially at rest, the velocity of the center of mass becomes 1 divided by 1 plus a multiplied by VL. Here, capital A is the mass of the target nucleus divided by the neutron mass. So this formula relates the velocity of the center of mass to the velocity of the neutron in the lab system. Secondly, we can derive the neutron velocity in the center of mass system, which is the velocity in the lab system minus the velocity of the center of mass itself. So the second formula relates the velocity of the neutron in the center of mass to the velocity of the neutron in the lab system. By substituting this expression in the first equation, we can also relate the velocity of the center of mass to the velocity of the neutron in the center of mass system. Finally, we can also relate the velocity of the target in the center of mass to the velocity of the neutron in the lab system. Previously, we have derived this relation, which says that the energy transfer in a collision and the change of direction in a collision are coupled to each other, and that the change in direction does only depend on the angle between the incoming and outgoing directions. E and E prime are the energies before and after the collision in the lab system, because that's what we are interested in. In a center of mass system, the energy before and after the collision would be the same. The probability to scatter over a certain angle can be expressed in either the lab system or the center of mass system, whatever suits us best. Usually, we will use the center of mass system for this, because scatter events are usually much more isotropic in the center of mass than they are in the lab system. Now we will derive a relation between the scattering angles in the lab system and in the center of mass system. Assume we have a neutron entering a collision with velocity VL and leaving the event with velocity VL prime. In the lab system, the scatter angle is theta L. In the center of mass system, the velocity before the collision is smaller and is called Vc, and the velocity after the collision is Vc prime. The scatter angle in the center of mass system is theta c, and the difference between the two red vectors after the collision is the center of mass velocity itself. Note again that the velocity of the neutron after the collision equals the velocity of the neutron before the collision in the center of mass system, but that in the lab system the velocity of the neutron after the collision is smaller than the velocity of the neutron before the collision. Using this diagram, we can relate the scattering angle in the lab system to that in the center of mass system. As a starting point, we can derive two expressions, shown here on the slide. The first one says that the two green lines shown in the figure should be equal to each other. While the second equation says that the bottom green line shown in the figure should be equal to the top green line and the velocity of the center of mass. If we use the relations between the velocities derived earlier and divide the two equations shown here on the slide, we get for the final result that tangent theta L equals sine theta c divided by cosine theta c plus 1 divided by capital A. And here capital A again is the mass of the target nucleus divided by the mass of the neutron. Using the same diagram, we can also relate the velocities of the neutron in the lab system before and after the collision. And via the velocities, we can also calculate the energies of the neutron before and after the collision. First, we have to realize that the angle between Vc prime and Vcm is pi minus theta c. Now we use the cosine law on the vectors Vc prime, Vcm and Vl prime to obtain the following relation. Here I've given the result of the cosine law again. We will simplify this equation by using the relations between the various velocities that we have derived before. In this way we can relate the velocity of the neutron in the center of mass system to the velocity of the neutron in the lab system. And we can also relate the velocity of the center of mass to the velocity of the neutron in the lab system. Furthermore, we will use that cosine pi minus theta c equals cosine theta c, and as a shorthand notation we will use mu c for this. Substituting all this In the first equation, we get for the ratio of the energies of the neutron after the collision and before the collision, the expression shown here on the slide. And the final result becomes E prime divided by E equals 1 plus alpha plus 1 minus alpha times mu c divided by 2. Here, alpha is the ratio of A minus 1 and A plus 1 squared, where capital A again is the mass of the target divided by the neutron mass. It has been tough, but we are almost there. There is one last step to make to relate the energy transfer in the lab system to the angle-dependent scatter cross-section in the center of mass system. For this, we use the fact that the probability for a neutron to scatter from E to E prime in the lab system must equal the probability to scatter over a certain angle in the center of mass system. And because the scatter angle does depend only on the polar angle between the incoming and outgoing directions, we can write this probability as a ratio of the scatter cross-section as a function of mu c divided by the total scatter cross-section. The next step is to relate dE prime and d mu c. And for this we use the result from the previous slide. There we found that E prime divided by E equals 1 plus alpha plus 1 minus alpha mu c divided by 2. Taking the derivative, we find for dE prime divided by d mu c the relation 1 minus alpha times E divided by 2. If we substitute this in the first equation, we get for the scatter probability from E to E prime the expression 2 divided by 1 minus alpha E multiplied by the scatter cross-section in the center of mass system over a certain angle mu c divided by the total scatter cross-section for the range between alpha E and E. The scatter probability is 0 elsewhere. Now there is one last assumption to make. If the scatter cross-section is isotropic in the center of mass system, which is actually a good approximation for neutron scattering with light nuclides, the scatter probability from E to E prime becomes simply 1 divided by 1 minus alpha E for the range between alpha E and 0 elsewhere. This means that a neutron can scatter with equal probability to any energy between alpha E and that it cannot scatter to energy below alpha E. This is a very important result we will use many times in reactor physics. Let's see how this works out in practice. This formula says that a neutron with energy E can scatter with equal probability to any energy between alpha E and but that it cannot scatter to energy below alpha E. If the target nucleus becomes lighter, the energy range of the scatter event becomes larger. Hydrogen, for example, has a value for alpha equal to 0, and the scatter energy range is the whole interval from E till 0. But if you have a very heavy nuclide, uranium for example, the energy range becomes very small, and the neutron needs many collisions to slow down from the fast energy region till the thermal energy range. Thank you for your attention, and if you have further questions, please contact us at the websites shown here.